Hello again. This is a Math Club reflection coming to you from the College of DuPage, and the title of this video is Elements of Mathematical Proof. As always, please be attentive while watching this video. By way of introduction, I proposed a challenge for you to prove or disprove the statement that a number is divisible by 7 if and only if the following condition holds. The difference between twice the unit digit of the given number, the remaining part of the given number should be a multiple of 7, or another multiple of 7 is 7 times 0. Now notice it does work here because, as we discussed, 7 goes into 2023 289 times, and 289 is 17 squared. So the prime factorization of 2023 is 7 times 17 squared. And also, 2 times the unit digit is 6, and the difference between 202 and 6 is 196, which is divisible by 7. So in our case, at least, we have confirmed that the difference between twice the unit digit and the rest of the number is divisible by 7. The number itself is also divisible by 7. But is it true in general? Now, if you came up with a counterexample, that would prove that it's not true. Proving that it's true can be more complicated. And when you think about mathematical proofs, one of the unavoidable questions is related to why do you do it? And one reason is to verify that the statement is true, but another one is because a proof helps us to understand the result and related concepts. And that's also why a new proof of a known result does add to the knowledge base and is of independent value. Proofs invariably involve statements of if and then, so we should discuss this a little bit. Compound statements of the form if P, then Q can be best understood as a promise. Truth for the whole compound sentence is decided on the basis of whether you think the promise is kept. Here, P and Q are themselves sentences or statements, each of which is true or false, but neither is both true and false. So think of this as a promise, and here's an example. If there is an element in the library, then I'll give you $100. Now suppose there really is an elephant in the library, and I give you $100. Then I've kept my promise, and the whole if-then statement is true. But suppose there really is an element in the library, but I don't give you any money. Then I've broken my promise, and the whole if-then statement is false. Now suppose there's no element in the library and I don't give you any money. I've kept my promise and the whole if-then statement is true. But what happens if there's no element in the library and I give you the $100 anyway? When I ask students in class about this, often half of them think I've broken the promise and half think I've kept it. Now, it can be ambiguous in ordinary English, but in technical sciences, mathematics, engineering, and so on and so forth, we view this as the promise being kept. So if P, then Q is true when P is false and Q is true. And so think of it this way. You're allowed to be generous in a promise and honest at the same time. The truth table below formalizes the discussion that we've had above. T stands for true and F stands for false. And note the third line is the case where ordinary English is not clear. But you see, if P, then Q is false only when a true implies a false. Now what happens if you interchange or commute the P and Q in an if-then statement? Now, this is called the converse. Generally get a statement with a different truth value. For example, here's a true if-then statement. If an animal is a bird, then it is a warm-blooded animal. That statement is always true. However, if you commute the if-then, it's false. Sometimes false, not reliably true. If an animal is warm-blooded, then it's a bird. Well, this is false about people. For example, people are warm-blooded but are not birds. So if we look at this, we can see that if P, then Q, and if Q, then P do not have the same truth values always. And that means that these are not logically equivalent. This is known as the fallacy of the converse. We also, in mathematics, frequently talk about statements that are if and only if, and in fact, the statement we're studying right now is if and only if. Now, these are true only when P and Q are both false or both true. And what that means is they have the same truth values. So P and Q, P if and only if Q, that means if P then Q, and if Q then P are both true. And so when you build the truth table, you get this. So the only time you get a true in the truth table is when they're both having the same truth value. Theorems that have the form P if and only if Q are much prized in mathematics. They give what are called necessary and sufficient conditions and are completely equivalent, and hopefully give you interesting and new ways to say exactly the same thing. For example, we can talk about a triangle being equilateral if all three sides are equal, but there was a theorem that says a triangle is equilateral if and only if all three angles are equal. Once this theorem is presented, there are at least two different ways to prove that something is or is not equilateral, working with lengths or with the sides of the angles. Okay, so let's turn to the problem at hand then. The following problem is for students who have a basic knowledge of proofs. You already have that from what I covered before. In particular, we were proving an if and only if statement. A if and only if B requires us to prove that A implies B and B implies A. And just to get started with another example, let n be the number we want to divide by 7, and B is the units digit, and the rest of the number is A. So you see, if we move the decimal point, we know that n, the number in question, is 10 times A plus B, where B is the units digit. Because all whole numbers n can be expressed as a product of 10 and a number added to its unit digit. So 983 is 10 times 98 plus 3, and 5896 is 10 times 598 plus 6, and so on, and we already talked about 2023. So we assign the following statements to A and B. Statement A is A minus 2B is divisible by 7, n. Statement B is n is divisible by 7. Now we have to show both that A implies B and B implies A. So let's begin with the first part. For one, we have to show that A implies B. That is, we have to show that A minus 2B is divisible by 7. If that is true, then n is divisible by 7. Okay, so let's begin. So assume, as we can, that if A minus 2B is divisible by 7, then we can find a natural number such that A minus 2B is equal to 7 times K, because the divisibility says there is no remainder. When you divide by 7, the remainder is 0, so it's 7 times K. Now we can take this expression and then multiply both sides by 10. That gives us 10A minus 20B is equal to 70K. And if we add B to both sides, we will have that 10A minus 20B plus B is 70K plus B. But now we can subtract the 20B from both sides, or actually we're subtracting minus 20B, so we're adding 20B to both sides. So going from this step to this step, we add 20B to both sides, and so we have 10A plus B is equal to 70K plus 21B. Notice that the left-hand side of our equation was what we called n, and the right-hand side is can be divided by 7. Therefore, this is divisible by 7. So we've assumed that A minus 2B is divisible by 7, and we've proven that n is divisible by 7. So we've proven our first step. Now for the second step, we have to show that B implies A. That is, we have to show that if n is divisible by 7, A minus 2B is divisible by 7. Okay, well, let's assume that n is divisible by 7, then, and we know this representation for n, 10A plus B is divisible by 7. So we can find a natural number, k, such that 10A plus B is equal to 7k. Now again, what we can do in this case is subtract 21b from both sides. So we take 21b from this side and 21b from this side. But that means that 10a minus 20b is equal to 7k minus 21b. Factoring on both sides, we get this. Now, since 10 is not divisible by 7, but this is a multiple of 7, that means that a minus 2b is divisible by 7. This proves the second statement, and we have now shown if n is divisible by 7, then a minus 2b is divisible by 7. So you see, we've shown that these two things are equivalent and proven the divisibility test. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself, because self-care is important. And now more than ever, take care of each other, because we're all in this together. Strive to make a difference. God bless you all. And these were the resources used in the video. Take care.